Hi everyone, it's my pleasure to present this work, Revisiting F-measure Optimization in Multi-Label Classification, a sampling-based approach. Let's start with the task. The input is a d-dimensional feature vector, and the label is a q-dimensional binary vector. Q is the number of labels. Our goal is to learn a classifier that predicts Y. There are many evaluation metrics for multi-label classification. In this paper, we focus on F-measure. It's the harmonic mean of precision and recall, so it works well when the label distribution is in balance. One common baseline is binary relevance. It makes label-wise decision by truncating probability as 0.5. This method works for Hamming accuracy well, but it does not optimize F-measure. A known result on optimal F-measure predictions comes from Dembski et al. Here, the sum of Yj represents the label volume, and the lambda j tau is the contribution score of the j's label when predicting with volume tau. However, applying this theorem brings two main difficulties. The first one is in training, estimating V, which has Q-square entries. The second one is in inference. Even after we estimate matrix B, computing lambda requires a matrix multiplication. Our first contribution speeds up the inference stage. The key observation is that matrix U has a constant screw diagonals. So by extracting these unique values into a long vector, we turn the multiplication into a convolution. This reduces complexity from cubic to q squared log q. The second contribution makes training more stable using a sample then estimates framework. In the literature, matrix V is estimated directly. First, fixing J, the sum of Vjk equals 1, which suggests a multinomial distribution. But in practice, MLC datasets are highly imbalanced, making this hard to train. So we take an indirect routine. Instead of estimating V directly, we estimate easier distribution that lets us sample labels. Then we can use Monte Carlo estimation on these samples to recover V. This essentially avoids training many multinomial estimators. In experiments, this method gives consistent gains across different datasets. Another benefit is that the same model can optimize other metrics like Hamming accuracy or subset accuracy. The optimal prediction rule are shown here. And the required quantities can also be computed by Monte Carlo estimation using the same label samples. This method contrasts with the prior approach, which require training a separate model for each metric.